So today we're very excited to have Simone Brugiapaglia from Concordia University. So he's an assistant professor at Concordia University. You did your bachelor's at University of Pisa, and also a PhD, a master's also at University of Pisa, and then a master's at Politecnico di Milano, and then a postdoc at EPFL. And then we were also postdocs for a year together at Simon Fraser with Ben Adcock. So today, Simone is going to talk to us about the mathematical foundations of deep learning, from rating impossibility to practical existence theorems.
Okay, yeah, thanks a lot, Nick. And thank you, everyone. I mean, it's been my first day here. Received a great hospitality, and yeah, full of meetings, and I've met many faculty members and students. Like it's been nice to talk. So yeah, thank you, especially Nick, for the kind invitation. So yeah, I would like to acknowledge, first of all, a list of collaborators that helped me achieve the results that I will tell you about today over the years. So there is Matthew Liu, an undergraduate student at Concordia, that is actually now working at Ubisoft. Weishi Wang is now a postdoctoral fellow at Concordia. We have Nick at Florida State. And some people that I started collaborating with during my postdoc at SFU, Ben Adcock, Sebastian Moraga is a PhD student at SFU, and Paul Tapper is a faculty member at SFU. Also Clayton Webster from the University of Texas at Austin. Also, I am grateful to the sources of funding that made this research possible over the years. Okay, we all know we are so-called AI golden age. Okay, that's a little plot taken from the 2022 AI Index report from Stanford. If you're curious, go out, check out the website. There are many interesting statistics related to AI and machine learning. That's the number of publications per year related to AI. So not only it's steadily increasing, but also the first derivative now seems to have been considerably increased in the last couple of years. And in particular, AI is a big topic. There's many sub-disciplines in it. And this other plot shows the breakdown number of publications per AI topic, subtopic in the last few years. And machine learning is the light blue curve. You see even there, like it's rising pretty fast. So yeah, I don't need to motivate too much, probably, that we are in front of a revolution. And we have seen, like today, I was picked up by department chair in a Tesla. You can try the automatic driving. So that's one of the applications of deep learning. So computer vision that apply to automatic driving, or even game playing. So particularly within machine learning, deep learning has had an impact in many sectors of industry, and more recently in research. So here I'm particular for this department in scientific computing. Okay, there's many people these days trying to leverage ideas from machine learning, and in particular deep learning, to maybe speed up or having more accurate simulation methods. For example, here some people are using deep learning to solve the high-dimensional partial differential equations, or to discover the governing laws of a dynamical system from time series data, and other problems. Like here there's an article recent from Science News, convergence of artificial intelligence, high performance computing, and simulations. So there's a lot of momentum in this at the intersection between these two areas, machine learning and scientific computing. However, there's the other side of the coin. There's also a lot of criticism about deep learning these days. In particular, deep learning is well known to be vulnerable to adversarial attacks. There are problem of instabilities of deep learning, in numerical instabilities. And if you think about it, applying this to medical imaging or medical applications in general could be very troublesome, because this might, of course, lead to incorrect diagnosis because of instabilities or medical frauds. So there is a lot of criticisms too. So particular, I like, this is a snapshot from a Science News paper recently that examined the role of instabilities in deep learning applied to medical imaging reconstruction from two researchers, Anders Hansen and Matthew Colbrook, and Berger Anton from Cambridge. They're really a big fan of. And if you think here, let me see if I can zoom. Yeah. So they cite this, the limits of AI, the Smail's 18th problem. So I was curious, and let's check out this Smail's 18th problem. And if you go back to the article, sorry, now I'll have to go back to the normal size. Okay. If you go to the Smail's article, Mathematical Problems for the Next Century, published in '98, actually it gives a list of 18 problems for so-called next century between pure and applied mathematics. And the last problem, problem 18, is about artificial intelligence. So I found this really visionary and like forward thinking. So the question is the following. Okay, first the title, Limits of Intelligence. What are the limits of intelligence, both artificial and human? And then I highlighted this passage because I think it was really ahead of its time. So Smail said, a broader study is called for, one which involves deeper models of the brain and of the computer in search of what artificial and human intelligence have in common and how they differ. I would look in a direction where learning, problem solving, and game theory play a substantial role, together with the mathematics of real numbers, approximation, probability, and geometry. So what I found really kind of visionary was the last part, where like was hoping for a highly interdisciplinary approach across the mathematical sciences to understand, to tackle the problem of artificial intelligence, because it's so complex that we need this kind of interdisciplinary approach. And so in this, sorry, this will go back, okay. In this talk, I will try to focus on this theme, the mathematical foundations of machine learning. And I will do that through an approach studying two particular case studies. One will be, there will be theorems involved, mostly a theoretical talk, but we'll try to put theorems about what deep learning can or cannot do. So the first case study will be so-called rating impossibility theorems. And the problem of interest is a so-called identity effect classification problem that we'll tell you about. So here we'll have a negative answer. We'll prove theorems that say when deep learning will always probably fail at performing a certain task. So no matter what learning algorithm you use, no matter how many epochs you train for, or things like that, like we probably know that in a setting, a certain task will be impossible. The second case study is practical existence theorems. That's a project in collaboration with Nick, Ben, and the SFU group. And here the focus is like parametric approximation, or in statistical terms, regression, where we instead will see a kind of a more positive answer. So proving theorems where you can see that deep learning can do at least as well as well-known approximation techniques for which we have convergence rates. And the two approaches, the two problems will also require different approaches. The first one will use mostly an elementary approach, and linear algebra, numerical linear algebra ideas, and multivariate calculus. For the second one, we'll need to combine things from different fields like compressed sensing, approximation theory, and deep neural network approximation theory in particular. So first of all, okay, probably if you're here, you have already heard of deep learning, but if you're new to the field, if you go to Google Scholar, Google deep learning, it's going to be a jungle, too many papers, it's really hard to get an orientation. I found these two papers very useful. One is an introductory paper published in Science Review, Deep Learning, an Introduction for Applied Mathematicians. That was a really, really gentle introduction and rigorous introduction to the topic that I highly recommend to students who want to know more kind of the rigorous foundations of the field, and like, because many papers are from a computer science perspective that could be hard to read if you come from math background. The second one is more about historical remarks, because this field is now like, it exploded in the past few years, but actually its origins go back to the 50s, if not earlier, when people were trying to build the so-called perceptron. That was the first kind of artificial intelligence machine that was trying to do a kind of this neural network idea. So just to set up notation and to make sure that we're on the same page, I will also define what do I mean by deep neural network and by deep learning. So the way I think about a feed-forward deep neural net is just a function approximator. Okay, you have a bunch of compositions of affine mappings, AJ, with nonlinear activations. So these affine mappings, AK, are associated with weight matrices WK plus bias terms, so-called bias terms BK. The activation function is applied component-wise to these intermediate vectors that are called hidden layers in the deep learning literature. And a very popular one is, for example, the ReLU, the rectified linear unit, which is just max between x and 0, but there are many other options proposed in the literature. And we know from numerical linear algebra or just linear algebra, you can interpret the matrix vector product as a graph. Like if you think about the non-zero edges of the matrix, that will build edges between the input vector and the output vector, and then you put weights on the edges by the corresponding edges of the matrix. So this will give you the graph type interpretation of the vector. Okay, but really mathematically it's just a bunch of nested, affine and component-wise nonlinear transformation. But this is what motivated at the beginning people to work in this field, because they wanted to, again, build a model for the brain. But of course, for the mathematics, we will need the algebraic description. And a bit of jargon, so people talk about the architecture of a deep neural network, so size of the input layer, of the output layers, the choice of the nonlinearity, the hidden layers, and so on. The depth, so deep learning, because the depth is the number of hidden layers that you have in the network. And training. So we talk about, these are deep neural networks, so we need to talk about deep learning. So there has to be some learning going on, and learning will happen through training. And you need to define the trainable parameters. This case will be all these weights and biases defining the affine transformations. And let's just call them, know that as a big vector theta, where you just vectorize all the trainable parameters. And then your network phi, that is the output, will depend, of course, on this big vector. The function phi will be a parametric function of the big vector theta. So we need to do deep learning, we need to perform training. Again, this is very basic stuff, but it will be useful later to set up the notation for the talk and like the setting. Now you need a training data. So you need examples to train the network. Okay, so this is the context of supervised learning. So we have pairs of input-output pairs, xi, yi, and we essentially everything boils down to solving an optimization problem that could be associated with minimizing certain possibly regularized loss function. Okay, so here I look for the best trainable parameters that best fit the data according to some loss function that will depend on the application. So typically, this loss function L will be a sum of these individual terms little l. And if this little l is just the absolute value of a difference squared, then you have the typical least squares fitting, or other people call the mean square error loss. You might have other type of losses like the cross entropy for classification problems. And another thing that will be important in the talk, the regularization. So you might want to enforce more structure on the coefficient, the trainable parameters, through a regularization term. So you have a penalty parameter, a tuning parameter lambda, that is non-negative plus a certain regularizer R. And typical examples could be R could be the LP norm of the vector. For example, if you minimize the L1 norm, this will promote sparse solutions. So this will enforce many weights to be 0 and only a few to be active. And yeah, that's an abstract optimization problem. And what you do then is, of course, we need method to solve that. Unfortunately, that's another open problem in the field, like what kind of methods will succeed to converge to find, well, finding a global minimum seems to be out of reach typically, but at least a good local minimum. But anyways, what people do empirically, they apply stochastic gradient descent, for example. That's the very first training method that you might want to apply, because in real world problem like computer vision, you might have many examples. So the parameter M might be of the order of millions, like millions images. So doing just one gradient iteration here might be too expensive. You need to instead to introduce this kind of batching process. So you divide the training set into batches, and you restrict the loss function only to some examples in a batch, and then you compute the gradient based only on that batch, and you just do gradient descent. Okay, so that typically the construction of these batches has some randomization going on. So that's why this gradient descent algorithm is stochastic, but that's just a setting to set the stage. And let's see like these two things. So first, gradient impossibility. I want to start with a question for the audience. So that I think should be easy, because for humans, this task is easy, but we'll see for machines it's not too easy. Suppose I tell you that the following words are good, A, A, G, G, L, L, M, M. The following words are bad, A, G, L, M, G, L, M, A. So who thinks that Y, Y is good? Who thinks that Y, Y is bad? Who thinks that Y, Z is good? Who thinks that Y, Z is bad? Right, perfect. 100% accuracy for humans. So machine learning works in human brain. However, we'll see that it's tricky for a machine, for deep learning, to learn this very simple task. I understand if two things are identical. So we'll call this an identity effect. And we'll like to see, because what you did now is you generalize outside the training set. When I asked you the question, I didn't show you any Y nor Z letter. I only show you A, G, L, M. But nonetheless, you were able to easily generalize to unseen examples because you were able to catch the pattern and just easily understand the what's going on when you were testing your hypothesis. So we'll see that machine learning algorithms, the story is a bit different. So this problem was initially motivated in linguistics, where people were trying to model where, for example, if artificial intelligence can understand where the sentence is grammatical, so there will be a certain structure of the word, or also in phonetics, phonology, where certain phonemes are allowable in certain languages, certain are not, and again, there's patterns in how the words sound. And experimentally, Gary Marcus in 1999 showed that even 7-month-old infants can generalize this type of identity effect. He probably went in the lab and tested this with very, very little kids. However, this generated a lot of discussion because he showed that neural networks could not learn this task. And then this triggered a huge discussion in the cognitive science community, where people who believe that neural networks could learn this kind of things are called connectionists, and the other one non-connectionists, where maybe there is something else going on in the brain, some kind of algebra-like structure that allowed your brain to understand the pattern. You can, if you want to go to YouTube, and you can see a recent debate between Yoshua Banjo in Montreal and Gary Marcus. Again, now the debate evolved a lot since then, but there's some fundamental disagreement about the potential of deep learning to capture algebraic type patterns. And let me set a bit of notation because we want to analyze this problem formally from a mathematical viewpoint. Okay, we call the set of admissible inputs X, and so there will be like 2-letter words. The example I showed you. Yes.
When you say the neural network cannot solve the problem, you follow the letters. Assuming how much data? I mean, assuming the data you showed.
I will show you that the amount of data will not matter, but you will not be able to generalize unseen examples. But I will tell you more about the data and also about how we will represent the data, because that will be a key aspect. Thank you for the question. By the way, feel free to interrupt me if you have questions. Okay. A young member of the audience has questions.
You generalize.
Yeah,
He's doing better than the machines.
Yeah, definitely. It's okay. We'll assign a rating to a word. Now, example 1 if the word is bad, 0 if the word is sorry, 1 if the word is good, 0 if the word is bad. In the example I showed you, X will be the universe of 2-letter words. And we're having a training data set. So the data I showed you before was this training data set. A couple of pairs with, and I was telling you bad or good, so 1 or 0. And then I will formalize the concept of a learner in this way. So calligraphic L would be a function that takes an input, the training data set, and a new input, and you want to assign a rating. Okay, so this type of formalism will be useful for this first problem. And this could be a neural network, could be even some simple classifier. It could be trained with SVD or other methods, Adams. For now, really, we're assuming a very abstract viewpoint at this stage. And you can prove this theorem. That's a very simple theorem to prove. I will be able to prove it today with you because it's a 1-line proof. You will see. So if you have a data set, that's so-called rating impossibility for invariant learners. So if you have a data set D and a transformation tau, that will be a key role in our analysis of the input space, assume that if you apply this transformation to the data isn't changed. And also assume that if you transform both the training data set and the new inputs, then the learner doesn't notice anything. Okay, so also the learner is invariant to this transformation tau. Then it's just one step to show that's the proof of the theorem. You use, if you want to show how the learner will be able to classify tau of x given the training data D, then essentially tau of x will be indistinguishable from x, essentially by using, it's almost a tautology. So in the first step, you use the invariance of the data because I replace D with tau D. In the second step, I use the invariance of the learner. And so at the end of the day, you will be assigning the same rating to x and tau x. You might be asking, okay, well, what do we make of this? It's too general. It's almost kind of useless. And we also thought that at the beginning, but actually this idea of having this transformation tau that makes the data and the learning invariant led us to a more interesting theorem, I believe, that now could deal with learners like deep neural network learners trained with SGD. So now assuming that you have a data set like inputs and ratings, and let's assume that you assign ratings are with a model of this form. That's a more general model than are deep neural networks. But what our model should do is like it takes the input, it multiplies by a matrix, and then it does something else. It could do, biases, nonlinearities, more layers, but it could even do something else. It's not necessarily a network, but this model includes deep forward networks. And V and W are trainable parameters. Then you can prove, so the key point of the previous theorem is that, okay, when does the invariance of the learner happen? Is this a reasonable hypothesis to, which learners will be invariant? So this theorem tells you exactly that if you consider this kind of model, and if you train them, again, by minimizing a regularized loss function via stochastic gradient descent, under a setting of technical assumption that I will tell you, then you can provably show invariance of the learner. So let's take a look at the statement. So first of all, we want our transformation tau of the input space to be linear and represented by an orthogonal matrix. Then we will train the trainable parameters by applying k iterations of SGD from a random initialization. That's something that people do very often in practice. They initialize the weights and the biases of the network random, and then they start iterating with SGD. And then we minimize with SGD the following regular wave pattern. Okay, so here we'll start seeing some constraints. So first of all, we are not allowed to regularize W in any ways to have this impossibility. So this kind of theorem can deal with this Frobenius norm, so kind of Tikhonov or Rich type regularization on the W parameters. But the regularization on the other parameters can be arbitrary. It can even be L1 or other type of regularizations, as soon as the whole regularized loss function is differentiable. Okay, so that's also, I think, a reasonable assumption. And also, yeah, the initialization should be independent for the W and V naught. And
A quick question.
yes,
But just to be technical, since this is a math talk, okay?
yes.
Is an OELU differentiable according to, based on, how does it, OELU strictly speaking is not differentiable.
Yeah.
So
That's a great technical. Yeah, to adapt that, you would need to, it's true. Actually, differentiability, you can lessen that. That's kind of the easier version. If you don't have differentiability at some points, you will need to do some kind of subgradient method.
Okay.
That can be extended. So yeah, to treat things like value, that's a good point. You need that. Other points? So, and if, okay, that's maybe the one of the assumptions that might sound a bit, it might make you a bit skeptical. So W naught times an orthogonal matrix would be equidistributed as W naught. However, if you assuming that W naught is a normal random Gaussian initialization, that this holds, because normal centered Gaussian variables essentially that they're going to be invariant. So invariant, their distribution will be invariant to orthogonal transformations. So that holds for Gaussian. But yeah, so under these technical assumptions, you can probably show that no matter how many iterations of SGD you will perform, no matter how you will regularize R, for example, the V term, no matter what kind of loss function you have, your learner will be invariant. And this can be extended like beyond non-differentiability with gradients. It can also be extended, for example, to the other algorithm and to other type of architectures that include recurrent neural networks, for example. And so let's go back to our, oh yeah, sorry, yeah, this is a loaded slide.
Make sure I follow. In the previous slide, tau was basically the identity on your data set, but here you're letting it be any linear transform.
Yeah, so I'm not claiming tau is the identity, but it leaves the data set unchecked. It might shuffle things in the data
On
set.
just the data set itself.
Yeah, on the whole data set.
But not on the space.
It might act on the data set, but
Competition theory.
yeah, it's just the data set is invariant, but it might not necessarily be the identity. There'll be some other type of transformation. And on the whole X, we'll see actually, I showed an example. The X will be essentially a kind of a symmetry, type of symmetry transformation.
And then,
so
but in the subsequent one, you're allowing tau to be anything now, or is this property still?
this is super general, but now tau should be linear and represented by an orthogonal matrix. So that's kind of, this orthogonality will be the key, and I'll show you the numerics too. If you have this kind of orthogonality, what I started calling it kind of the orthogonality barrier. No matter what kind of architecture depth you have, you will have this kind of invariance. It will be impossible to break it. There was a, yeah.
If that representation by T means the distribution is not changing, or is it like you augment your data set D such that it has T times Xi's inside it? So do you still work with the empirical data set, or
Actually T is not necessarily, actually not necessarily a random object. It will be a deterministic training data set. But I'm hiding you something at this stage because we'll be in the next two slides. I'm not telling you how I'm representing the data. You see here, X is just, okay, now this should be a vector space. But I'm not telling you really how I'm representing the inputs. That will be a key question, like how do we encode the inputs? And will be essentially related to what kind of trust matrix is associated with the transformation tau.
and I have another question about this gradient descent thing.
Yes.
So is it going to have a stationary distribution, the gradient descent that you're applying here?
So here, so here there's a little d. So actually here we're proving invariance in distribution. So because the previous theorem is like really hard equality. Now, since we have stochasticity in the SGD, we're proving that in distribution, the learner will always give you something with the same distribution. So it's kind of invariance in distribution.
Yes, that's a distribution of the data, but how about because when you apply gradient descent?
No, sorry, here there's not necessarily the data. So here the randomness comes from the random initialization.
But when you apply stochastic gradient descent with a fixed set of data, then your gradient converges to a distribution over V and W. Do you need that convergence, or?
No, here, even the number of iterations doesn't matter. You see, like here, I just fix any prescribed number of iterations. No, I'm not concerned about convergence of SGD. I'm just claiming SGD in this setting will give you always something that is invariant.
Irrespective of your batch size.
Sorry?
Independent of your batch size.
Yes.
And your learning rate can be anything?
Yeah, you can have it. If you want to have a learning rate that is random, then you have to assume independence on the learning rate with respect to all the other independent things. But otherwise, yeah, it can be deterministic. You can have a scheduler. No, thank you. These are excellent questions. Other curiosities? Okay. Okay, so let's go back to the easy example and see how this contextualizes in that example. So what does this transformation tau looks like to apply the theory? So that we have an orthogonal matrix associated with the transformation. This transformation will be very easy. So we have two letter words. Essentially what tau will do, if the second letter is a Y or a Z, it will switch them. Okay, if it's a Y, it will make it a Z. If it's a Z, it will make it a Y. In any other cases, if the second letter is not a Y nor a Z, it will just keep the word unchanged. So this tau, first of all, leaves the training set invariant, because remember, I never showed you y's or z's, the training sets. That was what I didn't show you. Therefore, this transformation will, it actually in this case will actually act as an identity on the data set, but not on the whole input space. However, there's a key question here. How do we encode the letters? Because we need to work with matrices and do linear algebra. So you need to pick up some vectors to represent, for example, in R26, because we have 26 letters, but that doesn't really matter. But in 26, that's a very canonical encoding that people use. It's called the one-hot encoding. So letter A is the vector E1, so 1, 0, 0, 0. Letter B is 0, 1, 0, 0, 0, and so on. Other type of encodings you might consider maybe an orthogonal basis of R26, or maybe just a linear independent encoding. So let's see what happens. You can actually write down what the transformation looks like with these encodings, because then you have a matrix. And this just essentially, this transformation will only switch two directions related to the encoding of one and z. That's why it's a symmetry. And if you have a canonical basis, the matrix T is just a permutation matrix, particularly is orthogonal. If the encoding is orthogonal, the permutation, the matrix T is an orthogonal matrix. So that will always give you an invariance of the learner. Linear independent, then you only know invertibility of the matrix T, and we cannot conclude invariance in that case. So last step, if L turns out, so if you're in a setting where we have invariance, then we know that essentially that we will not be able to distinguish tau x from x. In particular, if you let x be yz, then you cannot distinguish yy from yz. So that's probably show that, again, any learning algorithm in that setting will never be able to distinguish these two examples, because it didn't see that in the training set. Unless maybe there might be hope, we will see in the linear independent case. So where the encoding will favor some kind of redundancy in the way you represent letters, that might actually help.
Okay, so what I don't see yet, okay, is how tau fits into the neural network scheme. Like when you solve a neural network, fine, you get an answer, you can classify it, it works or it doesn't work. But where does tau fit in? I don't see.
Yeah, tau is like, if you think about it as an extra tool we need to prove invariance. It's like it's not like something that the problem gives you. It's an extra tool we need in this case to define a transformation that leaves the training set invariant. So there's no neural network here. On the other hand, there is a neural network here in the learner. Now, the learner in the previous theorem was a model of this form. So in this case, this will be the network. Okay, a function of some trainable parameter, and it's important that x enters linearly the first step. This might be a network. And then you can train that network using regularization, SGD, and in this case, and you will have, you will be in that setting. If you encode, for example, your letters as with the one-hot encoding, no matter how many iterations of SGD you do or how many layers you pick, that will have no impact on the invariance. That network will never see the difference between YY and YZ. So we'll not be able to generalize. So that's what, so tau is a device we use to essentially fool the network.
So in other words, if you say, so the theorem says, if you can find a transformation that has certain properties, then the neural network will not, and if the network satisfies properties, then you cannot.
Yes, yeah, it's a device. It's a device we use to fool, to construct an external example in a way that proves the non-generalizability.
Can I ask
Yes.
on the last slide,
The previous guess.
Yeah. So this tau, I mean, here seems to be entering through T, right? The matrix.
Yeah, T is the matrix associated with tau.
The only other place I see a T is in the initialization of
because
weights.
Yeah, so because at this stage we're dealing with matrices when you have W, but here when we're dealing with, so here in the input, we're assuming essentially when you use the encoding of the input, then you use the matrix. If you're assuming to have just an abstract representation, for example, letters, then you think about tau, the abstract tau. But as soon as there is an encoding of vectors, then you always use the matrix T. Okay, so I want to conclude this first part and with some numeric to show that actually we see this happening in practice too. So this is again a case where we train feed-forward neural networks, depth 1, 2, 3, but really you can go deeper. It doesn't help. And we encode, so the depth is from left to right. We are increasing the depth of the network. From top to bottom, we are changing the encoding of the letters. So it's top one hot, middle row orthogonal, bottom row distributed, so-called distributed encoding, which is just assigning a few random bits that are one. In this particular case, 3 random bits will be 1, and all the others will be 0. So there will not be orthogonality among the encoded vectors, but it will be linear independence with high probability. And okay, what are all these bars? So essentially the first 2 bars measure the performance of the neural networks in the training set. Okay, so we see the score assigned to AA, for example, here, and little y, little z is a random word that doesn't satisfy the identity. So these first 2 are examples in the training set. So the more we have like 1, 0 pattern, the better we do in the training set. However, all these examples are outside the training set because we haven't shown y and z to the network. And you see, for example, here, the scores that the networks assign to these letters to these words are always around 50%. There's no pattern where we can see, oh yeah, we're able to generalize the identity effect outside the training set if we use the one hot encoding. Similar for the orthogonal encoding. Here we're generating a random set of random orthogonal vector using the hard distribution. Again, the orthogonality barrier is not broken. However, if you use this distributed encoding, then this redundancy in the encoding makes it possible to learn, at least to a certain extent. The learning is not perfect, but at least we can start breaking the orthogonality barrier because we see a pattern here to YY and ZZ. So the fact that there is redundancy in the encoding helps generalizing.
What do you mean redundancy in the encoding?
Sorry?
I'm sorry, what do you mean by redundancy?
Redundancy, like is in the distributed encoding, every letter is represented with only 3 random bits at random positions that are 1, all the others are 0. Okay. So somehow when you do the one hot encoding, you only use 1 position for every letter. But now with the distributed one, you might use the same position for different letters because they overlap. They're not distinct anymore. You see, like A is represented by 3 random bits that are 1. The other 3 random bits, they might or might not overlap. So there might be redundancy in the position of the active bits. So this redundancy helps here. And then we have another example, a little bit more kind of machine learning type because there's computer vision involved. So here we combine 2 models, a computer vision model with an identity effect model. So now we don't want to recognize only identical 2-letter words, but we want to essentially classify palindromic numbers, 2-digit numbers. But I give you 2 images of handwritten digits, okay, from the popular MNIST data set. So I give you these 2 images, and I would like the machine learning system to tell me, do these 2 digits correspond to a palindromic number or not? So it's kind of, again, a palindromic in this case means just are the 2 digits identical? But now it's slightly different because the digit 9 can be represented by possibly many images. So we don't have just 1 9, 1 8, and so on. Until we want to see if we're able to generalize outside the training set when I don't show you 8 nor 9 in the training phase. I only show you digits from 0 to 7, but I would like the machine learning to generalize to 8 and 9s for the identity effect. So what we do now, we have 2 models, so we have to be a bit careful. So you see, I'm for some reason, Matthew, you, the student, I like to do this plot from right to left. Maybe how the human brain think about this twice, and like you go deeper. But the rating is assigned at the end, okay, on the left. So the inputs are the pairs of images that we have a computer vision model that converts this into vectors of probability. Okay, well, that's the first classifier. We'll tell you what is the probability that this is an 8. For example, here 8 seems to be the highest probability, even there might be some ambiguity here. In this case, the system is a bit uncertain between 3 and 5, for example, but the highest probability is 3. So there's a first model that classifies only individual digits. And then we combine these 2 classifiers within a model that is supposed to understand the identity effect, to spot the identity effect. So, and we have tried 2 things. because you have now to train the computer vision and the identity effect model. So we have considered an optimally trained computer vision model, and that's a computer vision model taken from a tutorial of Keras, the Python library. So if you use, for example, 12 epochs here in a certain setup, that's going to be the optimal training point for the computer vision model. But we also consider a ridiculously under-trained model, just one epoch, where the test loss for the computer vision will be larger, and see what's happened. So we're going to consider an under-trained and an optimally trained computer vision model. So now, what is the link with the previous case? So essentially, the computer vision model is creating the encoding. So think about these histograms as an encoding of this image. So I'm encoding this image into a vector of probabilities. Now, and the thing is, this is kind of a one-hot encoding, but with a bit of noise, essentially. In some cases, it might be a bit far from the one-hot encoding where the classifier is uncertain. So, and the other thing to notice is that the better I train the computer vision model, the closer this will be to a one-hot encoding. Because like, if the computer vision is very certain about a classification of a digit, it means that that probability will be very close to 1 or the other will be very close to 0. So when the computer model is optimally trained, then we have an encoding that is worse for the identity effect. This is very close to the one hot. If it's under-trained, though, we'll see that this noise, this extra noise, will help you to generalize the identity effect. So top row is overtrained. So let me undertrained, sorry. The top row is undertrained computer vision model. So we only do one epoch of the computer vision. So we have a very noisy one-hot encoding. Bottom row is an overtrained computer vision. So we have a very clean one-hot encoding. And again, we're moving the depth when we go to the right. And here we have a bit more things because there are images on the way. So you have two types of generalization. First of all, I never show digits of 8 nor 9 to the training. So these first two columns essentially measure the performance of images that were in the training set. They were from 0 to 8. Then we could have digits that were seen. For example, you might have trained with a certain bunch of 2, 3, and 4s, but now I try to classify a new pair of 2, 3, and 4. So in this case, it's generalization on the image level, not on the digit level. So these are the extra two bars, like 3 and 4. All the other bars is the performance at 8 and 9. So again, 8 and 9 was never seen by the training set in this model. So you see, interestingly, the performance is better. Again, we want this pattern to be this kind of differences between bars as pronounced as possible. The performance is better in the top row. That is the under-trained computer vision model. So if you don't train the computer vision well enough, well, the computer vision will be worse, but actually it will be easier to learn the identity effect because you're not too close for the one-hot encoding, which is bad for generalizing the identity effect. So then, philosophically, you can think about this in this way, like the computer vision is focusing on a detail, it's classifying one single digit. So if you focus too much on a single detail, you forget the big picture. You don't see the pattern, like the identity. On the other hand, maybe you don't know all the details perfectly of each image, but that makes you able to grasp the bigger picture. So there's maybe also a philosophical message in this little experiment. So okay, I will stop for questions here because now with time flies. So in the last 15 minutes, I will talk very quickly on the last project. Yeah.
Well, more than a question is a thought that the problem here that I see is by using the computer vision model, you lose the relationship between the numbers. Right? The better your computer vision model is, when you become just one hot encoded vector, then the network doesn't have any relationship between the numbers that it hasn't seen. It would be better to classify directly from the two images directly, because in that way, there is some relationship between the first numbers from 0 to 7 with 8 and 9. Yeah. By putting the first step of the computer vision model
No, that's a good point.
Making
Yeah,
a hot vector.
Yeah.
Then the network doesn't know any relationship between the other numbers. That's
yeah,
how I see it.
I agree with you. That's exactly what intuitively that's what's going on. And especially if you never show 8 and 9 with the one hot encoding, you will never activate these two things. But yeah, that's a fair point. So I totally agree. So we haven't tried with the full kind of just one big model, because in that case, maybe one should have to look at the intermediate layers to see what the encodings are, maybe at the intermediate layers. That's something interesting. We haven't tried that. But yeah, in this case, it's true what you're saying. So in the one hot encoding, if you never see 8 or 9s, you will barely activate these two. But even if you the fact that the real key here, we wanted to try this on something different than the alphabet. So we came up with this example, but I agree with you. There are ways we kind of wanted to verify this impossibility in a different framework that is kind of one hot with noise. But yeah, if I had to really solve this and make the job, probably, yeah, I would train one single model. But keep in mind that the real barrier is the orthogonality. It's not even do we ever, because that was shown with the letter example. Even if you have an orthogonal encoding where you activate the encoding activates all the units, still the network is not able to break the orthogonality barrier. So yeah, in a way, the one hot is really intuitive because you never touch certain units. But even if you touch all of them, orthogonality is the real barrier. Okay, so I want to say, yeah, I have way less. I have maybe 2 minutes. I don't know how many minutes I have. Let you tell me.
About 10 minutes, yeah.
10? Okay. Okay, maybe I'll do a quick tour. Maybe you can, that's stuff that collaboration with Nick, so maybe you already heard, and you can ask Nick when I'll go away. So I'll be a bit quicker on the practical existence there. So the rating impossibility was a setting where we're able to provide negative answers to the question, like, can deep learning solve a certain simple task under certain conditions? Now let's take a look at what you can do in a positive sense. So here the framework is the function approximation. We want to approximate a high-dimensional function f given some pointwise sample. So typically this is motivated by surrogate modeling or assertive unification. That's something that I guess several people in the audience might be already familiar with. So an example could be parametric PDE. So you have an input that will be the parameters of your PDE. Then you have a model, could be a numerical PDE solver that will generate a solution to the PDE given the parameters. So this F will be a solution map, like mapping the PDE parameters to the PDE solution. And yeah, there's this nice book where assertive unification where there's many applications discussed for different models ranging from weather, climate, and biology. And so what you can do here is what many people have proposed is doing polynomial approximation. Okay, so you might set up an orthogonal polynomial basis on the interval, assuming that you are in a hypercube, and then you tensorize your orthogonal polynomials. Okay, so if you tensorize things in 2D, that will look like this. Okay, you're tensorizing parabolas with parabolas with line and things like that. So you have a multidimensional orthogonal polynomial basis, like the Legendre basis, for example. And we'd like to construct, you can expand the function with respect to this basis, and we'd like us to construct a sparse approximation. So that is to say an approximation where only a few coefficients are activated. I will skip very quickly here, but essentially you can prove rigorous approximation bounds for S sparse approximations. So if you use S terms and your function is smooth enough, and smooth enough would mean holomorphic or analytic in a Bernstein polyellipse, then you can formally prove that there are exponential convergent rates of this type of polynomial approximation with respect to the sparsity. And this happens in a large class of parametric models. So essentially, you can tackle these approximation problems in many ways, including more or less classical ones, like maybe interpolation via sparse grids or Monte Carlo quadrature or other quadrature methods, least squares. In this case, I will talk about compressed sensing, and in particular, how compressed sensing that has theory for convergence can inform the theory for convergence when you want to approximate with deep learning, so non-polynomial basis. And yeah, sorry, maybe that's a bit technical for the last minutes, but essentially for the compressed sensing, what you do, you sample the polynomials at the sampling point. So you build the sampling matrix A, you sample the function at the sampling points, you build the right-hand side, and you solve typically a lasso type problem. In this case, it's a square lasso because it has beneficial properties in terms of tuning the parameter lambda. And so again, like in the initial case, you balance data fidelity with some kind of regularization term. In this case, it's a weighted sparsity regularizer that is supposed to promote not only sparse solutions, but sparse solutions where the sparsity has a certain pattern. So the beauty of this method is that, okay, many people work on that. Here we have including Nick, Ben, and several other very, very nice researchers before us. But the beauty of this is that you can prove rigorous convergence rates. So now remember the exponential convergence rates for the best approximation you can get with S terms. Well, you can prove similar convergence rates for a compressed sensing approximation. Let's say if you use M samples and you're trying to approximate a very smooth function, a holomorphic function, then you can prove if you pick the polynomial space well enough using this hyperbolic cross space, you can prove that you have the same type of exponential convergence rates in the number of samples modified up to log factors as the optimal approximation. So this beautiful result, it's a fruit of years of research. If you're curious to know more, is also available in this recently, that's a shameless plug. It's my recently published book with Ben and Clayton, Sparse polynomial approximation of high dimensional function. And so I have a companion website. But what I wanted to tell you quickly about is why this is relevant to deep learning. Because people typically, when you approximate a function with deep learning, there's many theorems that are so-called universal approximation theorems, where you fix a class of functions and you typically show then there exists a network that approximates functions in that class up to an arbitrary accuracy of psi. So what this type of universal approximation theorems don't tell you is like how much data you need to construct that approximation. How do you train the network to construct that approximation? So again, in collaboration with Nick, Ben, and Sebastian, it's possible to have results, so-called practical existence theorems. So the first version was proposed by Nick and Ben in 2021 in a slightly different form, and then we extended this also to Hilbert-valued functions where you approximate whole solutions maps to PDEs. And essentially now, under a similar setting of the copper sensing setting, you can show that you can approximate holomorphic functions from M samples in a way that essentially achieves the same type of exponential convergence rates as the compressed sensing ones. But the novelty is that you can give bounds on how deep, how many trainable parameters you should have, and the so-called size of the network. All this scales polynomially with respect to the sample complexity up to log factors. And also you have an input and hint on how you should regularize the training. So this result, I don't have time to show the sketch of the proof. I'm happy to discuss these days if you're interested. But essentially, it's a link between compressed sensing and deep learning, because the idea is to first construct deep neural networks that approximate polynomials. And then in a second step, link the training algorithm for deep learning with the training algorithm with compressed sensing to then leverage the theory for compressed sensing that we know and get the exponential rates. So this type of result, now it's a positive one, because it tells us that how much, if you're given M data points, we're able to achieve known conversion rates that are as good as a state-of-the-art method like compressed sensing. Maybe you could do better, but at least you know you will do, with this amount of data, you will do as well as compressed sensing. And okay, I'll skip the numerics in the interest of time and just quickly mention that it's a work in progress to apply this also to high-dimensional PDEs. So numerical methods for PDEs defined on a high-dimensional domain. And I will just conclude here. Hopefully, I'll show you a kind of two cases where we, inspired by Ismail's work, we will try to investigate mathematical foundations of deep learning, and in particular, identify limitations and potential of deep learning. I think both are important. Sometimes limitations are even more important the potential. But yeah, we only scratched the surface. Hopefully, this inspire you to ask more questions, and I'm happy to chat these days. Thank you very much for the attention.